Welcome to let's try that again. Welcome to two-dimensional motion in vectors. This is chapter 3. This will cover section 2. There are about 16 slides, most of which is really a running example, or 2 actually. And this is part 2 of a 4-part series. Part 3 will slow down just a little bit, and part 4 will go very quickly. This is a little bit more review for you. You may not need much out of this presentation, so fortunately it should be fairly short. In any case, you may want to review it, look through the slides, see if something looks unusual to you and you haven't read the chapter. Maybe you watch the presentation from at least a certain part, but that'll be up to you. Presentation is here for you. Okay, let's move on. Here we have the objectives coming out of section 2 of chapter 3. This would be coordinating with our unit 6 actually, where we would review some of these topics, but we would really kind of jump into projectile motion, which is what section 3 is about. So you just want to understand using a coordinate system. That's your XY scale, XY axes coordinate system and scale if you're doing it manually. We want to be able to apply the Pythagorean theorem, and we want to be able to resolve vectors using our trig functions rather than always having to resort to a piece of graph paper, which is nice, you know, that you can do it manually, but really many times, you know, you just want to jump right to the math and crunch the numbers, set it up, and make sure that you have values that you need going forward to solve the problem. Okay, so Pythagorean theorem, that's all this is just a review of that. You can pause for a moment and take a look at the slide if it helps. If we want to find the angle of a resultant, remember, which is really the hypotenuse of vector addition or vector subtraction, it still results in a hypotenuse. And so we can use tangent, although you can use other functions depending on what you know about the motion, whether it's to any vector, which is could be displacement, could be acceleration, could be velocity, could be forces. Regardless of what the vector quantity is, depending on what you know, you may be able to use sine or cosine functions as well in order to resolve the angle. In this case, what I found at the time I created this slide is I was using the inverse tangent quite a bit in order to find angles. I would encourage you to double check your calculators to make sure they're set on degrees when you're doing this, because we're set up for degrees, not radians, with what we are talking about. Okay, let's check out example 3a. This might coordinate with your book in chapter 3, section 2, problem set A. So here we have, okay, it is page 90. We have a y value of 136 meters, an x value, half of the width of the pyramid, 115 meters. What is the magnitude and direction of an archaeologist climbing up the side of a pyramid? So what can we do here? Well, if we want to find, because we have the height and we have the width, then we can actually find the length of the side of a pyramid. And plugging the numbers in, you can find, obviously, square root to find the displacement squared, or the square of the displacement. If you want to find the angle, because we know both the opposite and adjacent sides, we can use the inverse tangent function. And that would give us the angle of the pitch of the side of the pyramid. And that would be a little under 50 degrees. So that would be at least with these numbers, that would be a fairly difficult climb. Fortunately, the pyramids, while they may used to have been very smooth-sided, of course, over 3,000 years, that much of that whatever they coated the pyramids with, I want to say it was like maybe a type of mortar. It wasn't just compacted sand. That's all worn away, and so it's much easier to climb, although illegal to climb the pyramids these days. It's much easier to climb them because of all the nooks, crannies, footholds, etc. Even in many cases, it's almost like a big set of stairs. Okay, resolving vectors into components. Remember that we can take any vector and treat it as a resultant and then describe it in terms of perpendicular components. We call x and y arbitrarily. For example, you're on a movie set as a cameraman. You're going to be in a truck filming an overhead plane. The plane will be flying at 95 kilometers per hour at an angle of 20 degrees relative to the ground. So, you know, flying up as if they may have just taken off. How fast does the truck have to go to stay exactly under the plane. Well, basically, if you know that the plane is flying on that angle of 95 kilometers per hour, that's the resultant. What you need is the horizontal component, and once you know the horizontal component, that's how fast the truck has to go to stay exactly with the plane, because moving in the out direction as opposed to out and up, in the out direction, that is the ground speed of the plane itself, regardless of its altitude change. And so it's that easy. And if you are on a movie set and you're coordinating all of that, honestly, someone is crunching the physics to make sure that that truck, that camera dolly, that whatever is exactly where they need to be. It's science. You know, they may have fancy formulas for it, but it's science. It's physics. So we can, of course, use sine and cosine functions, and you can look at this slide. These are things we've already done before. So pause, take a look if you need to. Same thing here, just talking about the cosine of the angle with respect to that plane and the cameraman in the truck, or camera person in the truck. And so it looks like that truck needs to be just traveling under, just slightly over 89 kilometers per hour, moving directly to the east. If you do that, you'll stay with the plane and keep the plane in frame, if you will. Okay, example 3b. So what are the horizontal and vertical components of Superman, who flies down from a building top at which is, I guess, 125 meters above the ground at an angle of 25 degrees below the horizontal? Okay, so there's my building, there's the trajectory of Superman, and what am I looking for? Well, I'm looking for how far out and how far down. I guess 125 meters is the actual resultant. I misspoke a moment ago thinking that was the height of the building top, but that's actually Superman's path. So he traveled the resultant, so 125 is the resultant. Well, if I want to know how far out Superman lands, if I want to know how far Superman came down from the top of the building, I would simply plug the trig in. If I did that, this is what I would find, and this is, of course, measured below the building. So d is the height, or dy. Dx, of course, would be the out part. Example 3c. Adding vectors that are not perpendicular can be done by resolving all vectors into x and y components and then adding these things together to obtain a total. So 3c, for example, a plane flies 50 kilometers at 35 degrees above the ground, then does something different. It climbs at 10 degrees for another 220 kilometers. The question eventually is, what's the magnitude of the plane's displacement, meaning what is the overall resultant? And probably when the resultant is asked for, then you also are asked to find the angle of the resultant with respect to whatever reference point is decided upon. Okay, so here's the example again. Let's diagram what's happening, and I think I'm supposed to activate my pen and do a quick sketch for you. So here we go. And I guess I can choose white at this point. So the first thing we have our plane starting here, and of course I have like an XY coordinate system. It's going to go 50 kilometers at 35 degrees above the ground. So I think I can actually lay that down and do this. Give myself a little bit of a straight line. I'm actually tracing. All right, so there we go. This would be, well, that seems a little bit shallow. So let's try that again. I think I do just a little bit better here. I was focused on trying to get the protractor correct. But in the end, let's freehand it. So 35 degrees is probably more like that. And we'll say that's 50 kilometers, so whatever the length of that is. Then at this point, because I'm going to add these vectors together, so I just think about another XYZ coordinate system, now I'm going to be at 10 degrees, which is a very shallow angle, but I want to go 220 kilometers, which is about 4 times the length of this. And so, shallow angle, and 4 times the length of that might look more like that. So here are both vectors. I have roughly a 10-degree angle there, roughly a 35-degree angle there. This would represent 50, that would represent 220. And my resultant would be measured from, let me change my ink color here, from this point to that point. You draw that line in, there's your resultant. You measure whatever that angle is, and there's your angle of your resultant. Let's see where this goes. Okay, so a little bit better drawn up on top is just the two vectors, and then I've created kind of a big triangle showing both of those components kind of spread out. Well, D1 and D2 representing each part of the displacement. You can see the trig down below. The first part of the trip down here, so this is the first part with the 50 kilometers and the, I guess it was a 35-degree angle. Down here, if I want to know how high it went in the first part of the trip, here is the height. So that would cover, let's see, up in here, if I want to, that would cover this part and this part of the trip. So that's how far out, and then way over here, that far up, right in there. So that's what that is going to cover. In the second part of the trip, this is your 220 kilometers, but it's only a 10-degree angle. Here again, 220 kilometers, only a 10-degree angle. This will get you how far out, and this will get you how far up during that part of the trip. So the how far out will cover actually all of this because it's that part of the trip. It's that triangle. The up in number 2 here is this part of the up. You add both of these together, that's how far total up you are, and if you add this part of the out and this part of the out together, then you have the entire out. Not overly technical. And then if you want to know the angle of the resultant would be pretty much that angle right there. And let's see where it goes. So solving it, it's a total of 227 kilometers out if I wanted to quickly label my diagram. So there's 227 kilometers. And you're going to have an altitude of 66.9 kilometers up all the way to here. Then what? 14 degrees. So this angle here is 14.6 degrees. And actually, I could even solve for my resultant itself because I don't have my resultant. What I have is the sum of all of this in component form. What could I do? Well, I could actually find the resultant. And how did I do that? Well, actually, I just used Pythagorean's theorem. It was that quick because I knew both sides. But you have the angles, so sine and cosine would be optional as well. So there's your resultant. So what did the plane actually do? Well, it attained an overall altitude of 66.9 kilometers. It traveled from the point of taking off to wherever we measured it. It traveled a total of 257 kilometers on land, kind of land miles, or land distance. And then the actual, what the plane logged was 266 kilometers of flight displacement, because that's the actual path of the plane. Okay, moving on. Okay, this represents the last slide in this very short presentation, and what I would like to do is just let you know that in part 3, while the first 2 parts here have been by and large review, hopefully they were helpful, you may not have needed any of it. Either way, it was there, right? But what I would like to let you know is in part 3 we're going to be dealing with projectiles. And I would strongly encourage you to read that part of the chapter, chapter 3, section 3, and projectiles very quickly. If I can use this slide, I'll just sketch here really quick. So if I have, say, a cliff, and I have a rock on that cliff, and someone's standing up here, here I am, and I kick the rock, and the rock basically just travels out, and oh, that is horrible. So I think I can try that again. It's I guess my OCD kicking in, as far as just needing it to look a little bit better. But anyway, just kind of travels down, 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 and then hits the bottom here somewhere. So in this particular case, this is a projectile. It's only really half of a projectile, but it's a projectile because it didn't go up and out, it just went out and down. And it turns out that the out and the down parts of the motion are separate from each other. The out is based on really the force of whatever got this rock moving and gave it acceleration, and that is constant. Once the force is employed and the object starts moving, obviously the force is gone because your foot doesn't stay in contact with the rock, and so the velocity then in the x direction is basically constant. It doesn't change. whereas the vertical motion is controlled by the force of gravity, and so you'll considerably change your velocity in the downwards direction, and you will experience acceleration due to gravity. And so you'll fall faster and faster and faster and faster. And that's why you have a fairly flat level of flight at the beginning, but then it really dramatically becomes vertical at the end of the motion because gravity has caused you to accelerate so rapidly that you have a lot of vertical change in motion for the same amount of x. In any case, this is projectile, or if you want, imagine throwing a baseball from the outfield in, right? Travels something like that. Well, there it is. This is the rock. And then this is just pre-rock. This is just what happened before the rock, right? So it's like basically mirror images of the same motion, if indeed it starts and ends at the same spot. So half of the baseball throw is similar to this rock motion over here, and we can draw some analogies back and forth between them. And that'll be all section 3, but I wanted to preview it if you were listening to this video and you got this far, that there's the preview. Thank you, and I will see you in part 3.